Perfect.
LLMs and knowledge graphs, Mrinal Mathur. Go ahead and present.
All right, thank you so much. So good morning, everyone. Today I'm going to present my presentation on exploring behavior recommendation using large language models and knowledge graph. This presentation is actually going to touch upon a lot of basics of large language models and how you can do prompting as well. But I won't deep dive on any of these techniques right now because there's a lot to cover even in the sense of knowledge graphs and LLMs. But feel free to just stop me, and if you have any doubts or anything, I'll clarify at that moment. So saying that, I'll just go towards why we want to build on this presentation. So the motivation in this is like in our daily lives, the interactions with AI assistants, like for example Alexa or Siri, have been very useful for day-to-day tasks. And in order for you to respond to a simple voice command and perform basic tasks, it's becoming more of a day job right now. So for example, if you want to set a timer, what's the weather, etc. And there are a lot of users who are using these AI assistants for performing multiple tasks where they respond to the user request, and we also wanted to observe that as we are using this, the expectation of humans are actually increasing, and so we engage in a more diverse manner with these AI assistants. Because of which we may require some personalized daily routines, for example, like calling someone or turning off the lights in the dining room. So this project actually aims to evolve in so that we can make this Alexa into a more proactive assistant, and we can also use it in such a way that we can recommend the customer's need based on their interaction history, and therefore also offering a more intuitive and engaging experience so that you can have a more personal recommendation. So for that, we also want to utilize like recent large language models to predict and to recommend behaviors of the users by analyzing the interaction that customers have with AI assistants, in this case, Alexa or Siri. So before I move to the actual implementation, a few background that is actually important for us to know, and that we should familiar with as well. So traditional recommender system are based on like clustering approaches. So few of them which are like collaborative filtering, which try to match users with context or with each other using matrix factorization to identify the relationship between your items and the user entities. So this is definitely a very simple method, but the sparse nature of user item matrix is actually very difficult to calculate. So because of the issue related to collaborative filtering, we move on to a more sequential recommendation where you can use okay, just give me, yeah. So where you can use each of the items or each of the blocks in order to identify which actions are important and which should move sequentially. And sequential recommendation is also viewed as a next item prediction task, where the goal is to just to predict the user's next action or based on their past action sequences. But the problem is again that you're not able to capture long-term patterns of user by simply combining, these information from different sessions. So we move on to a better recommendation just for checking out. So in this case, this paper behavior sequence for e-commerce recommendation by Alibaba, they are just using a transformer layer instead of just simple RNNs in order to mitigate those long sequence problem. But the early fusion and action type embeddings are actually effective when dealing with sequential features. But the problem in this case is, yeah, so this is like one of the limitation. The second limitation is like the positional information does not really add much value when you're using the transformer layer. So the third way which we wanted to use was kind of a complicated part, which actually introduces a hybrid approach for ranking, which combines end-to-end sequential modeling by transformers and also some embedding layer for batch generated user embeddings. And that actually gave a very good result in terms of all the other next action prediction models. So we wanted to define a problem in this case where given a user interaction, can we predict the behavior of for a particular week on any specific day? And the question is posed such a way that the user recommendation is useful, so that we can also provide them with relevant recommendation based on their daily behaviors. And I'll explain like what I'm saying this word behaviors and actions again and again, but what exactly are actions and behaviors? So action are something, user action can be defined by a predefined set of activities that you do in a sequence, but the behaviors are defined as the repeated occurrences of the similar actions that concurrently happen every day. So in this case, as you can see the example, the snooze the alarm is happening every day from Monday, Tuesday, Wednesday at 7 a.m. So that's a behavior that we have. And similarly, if we see on 9 a.m. For Monday and Wednesday, play some music, that's also a behavior from one particular customer. So we wanted to capture that. So in order to do that, we had this data set, the user Alexa interaction data set that gives us these these are basically the internal interaction with the with Alexa. So in this case, we have only sampled the 2 weeks of the current analysis, and uh I've actually analyzed the feature and just extracted few of those which you can see here. So few of them are the day of the week, the hour format, the intent of this case, and the request. Requests are the basically the what the user is actually asking Alexa or Siri to do. So in this case, just to give you an example, the intent in this case is play music intent, and user has requested to play music or play more music like this. And the second one is like turn all the lights off for this week, which is week 40. And this is Saturday, and this is happening on Sunday. So we have this information, right? And not only that, but we have like a plethora of information in this case. So, in order for us to extract meaningful information, meaningful features from this traffic data, we need to use some machine learning model performance in order for us to extract meaningful features from this traffic data for any machine learning model performance, we are using temporal features, text features, and intent types. So the temporal features are very basic, where you can just use it the week, the day, and weekend if it's a weekend or not. The text features are all the requests that you are doing with that you are making with the AI assistants, and the intent type where basically you're just clustering all those text features in just one particular group. So in this case, it can be like play music, weather intent, or notification. So we did some EDA in this case, exploratory data analysis, and we found out that the categories of day of the week are actually interesting to see, because we can see like the engagement of users is high during Sunday and Monday, but lower towards Wednesday and Friday. So that's something which is very interesting to see, because we can see the frequency of certain we can also see this frequency of certain words, uh, which is where it is. Yeah. Yeah. Frequency of specific words, which indicates that the customer preferences for regular activities. So in this case, you can see that the most frequent uh, request that is coming from the customer is about play. So you can say anything like play some music, play some video or something like that, and that is the highest frequency of the group as well that is being used. So the takeaway from this is like, yeah, we have interaction, we have plethora of interaction data with in Alexa, but what can we do in order to, in order to capture these information? So the first baseline which I tried was using just BERT, which is going to select the features that we already have and do a next action prediction based on what the user will be requesting. And in that case, what we saw was it was not great to understand the context. And we also saw less sequential accuracy, exact match, and F1 score. So what that tells us is that using smaller models does not actually generalize well for this particular case. So it's better to investigate and explore, better pre-trained large models. And that's where we bring the large models in this case. So LLMs, I guess everybody here is familiar with what LLMs are. But just to give you context in this, so large language models are actually much better in understanding and generating human-like text right now. And these are the decoder type models. For example, GPT, Cloud, Llama, and all those things. And they also have a better, richer data representation, which is useful for this particular case. So we wanted to propose this method where we are using the extracted features, and we use some these extracted features to do some prompt engineering. As you can see, we just putting it in a more, and natural language text, which is on a Monday of week 40 at 7 a.m. The user asked to set a 2-minute timer. And then using this prompt, we can actually we actually input this into the large language model and give us the output for the next action or next behavior in that case. That seems very simple in this case, because the only thing that we are trying to do is we're just trying to input the prompt from the feature engineering, put it to LLM, and just give us the next behavior in this case. And this particular proposed method is only used so that we can analyze on what type of prompting method will be useful for the proposed method that I'll be discussing in the upcoming slides. So, for those who are not familiar with what prompt styling is, we propose two style of prompting for with the large language model. The first is the zero-shot prompting, and second is K-shot prompting or few-shot prompting. So zero-shot prompting is exactly what we are trying to do with current GPTs or Chat GPT or any cloud model, where we just enter the prompt and it should give us the answer right away. Yeah, it should give us the answer right away. So yeah, so this is the architecture for that we wanted to check. Just give me a moment.
So wait a second. Prompt styling is this pattern matching way of asking to complete this string, right?
Yes, yes. So the prompt styling in this case, we are just checking which sorry, yeah. So in this case, the only thing that we are doing in this case is just giving one prompt to the pre-trained model that we already have, which is, let's say in this case, Llama 7B, and we are asking that Llama 7B to just tell me like what the next model or next action is going to be for that particular.
What you have on the screen, is that the prompt? So you're
No, no,
giving
no.
few
That is
patterns.
just that is just an example of what prompting is. So in this case, so this is a case short prompting where you're giving the examples in this case. So we're giving the positive, neutral, and negative examples already. You're showing it already to the large language model, and then you're asking that LLM what should be the answer for this particular prompt.
You're not asking anything, right? This is the prompt, right?
Yeah,
Like
this is
the prompt goes up to the last two slashes, right? And then LLM
so.
continues
So there
string.
are two. So actually, if I just look into it like this, if I just give this whole particular prompt,
Mhm.
right, then this is just like one shot. Or sorry, not even one shot. This is just zero shot. So what one shot, two shot, three K shot is, you have to show uh, the question. So it's like this. You have to X1, you have to show LLM what X1 and Y1 is. X1 in this case is the prompt where it says circulation revenue has increased by 5% in Finland, and the Y1 is positive. Just like that, you have to show LLMs few examples. So in this case, I'm showing 3 examples, and then I'm
Within a
expecting
single prompt, right?
into a single prompt, right?
Within a single prompt. Yeah. So
Yes,
you're
yes,
saying, okay, here's the string with A comma B D comma C, etc., and
yeah,
now you're saying F comma, and it
yes,
just
yes,
completes the string. And
yes.
that's zero shot. So
That's zero shot.
why is it called styling, and how does K shot work?
Right. So I'm going to okay. So styling in that case, what happens is like we also have to make sure we're giving the system prompt for this. So in the system prompt that I can show you in the next slide. So for example, yeah, so these are the types of prompt which I have given. So let's say this is just like zero shot in this case, because I'm just giving like one particular example. And the system prompt in this case is just asking like what given the past interaction, can you suggest me some next personalized action for this, which aligns with the prompt? So that is the styling which I'm talking about. The styling changes as soon as you are changing this system prompt, and it might give you different answers as well. So that's where the prompt
This new
engineering.
prompt is your styling, styling, right?
Yeah. Uh, yeah, I mean, yeah, we can say that. Yeah.
Okay. Just, just trying to digest things, what is styling. And you will talk about K-short.
Yes, yes, yes. And in the upcoming slides, I'll be talking about K-shots as well.
Okay.
So, yeah, so coming here, so we are doing this zero shot prompting where we're giving just few examples and asking my LLM to just give me the next action prediction in this case. So you can see it's giving me a next action, which is very close to what the current prompts are, but it's not exactly, correct. So that is one case, but the other case is how do we evaluate our output? So let's say our references are, and this is going to be very important in any LLM based problems, because the evaluation is a very important part, because we are not just exactly using the natural language output. We also need to make sure we are capturing all the essence of the actual feature which we are taking into consideration. So in this case, the reference in this case is like on Friday of week 40 around 7 p.m. The user requested to order sushi, and in the output, the only thing that is changing is the time, and the user requested to order dinner. But now the discrepancy is that these two timings are not exactly matching. The time might not match, but in the case of the context, which is order sushi and to order dinner, they're contextually same, but then the actual wordings might be different. Because of which, if you're using some evaluation metrics like exact match, which is a very strict form of evaluation, it will give us zero, and that you will be seeing in the later slides as well. So in this case, but this gives us some insight on what type of on what type of relationship do we have in our case. So the learning input output relationship that can be casted as a next action prediction in this case is called the in context learning. And in context learning is where we will be going towards the few shot learning. So given the examples, as I mentioned before, you'll be giving some examples in order to show how LLMs should be giving you the answers as well, and then you will be giving the prompt as given in this example. So the task description is translate the English to French, and then you'll be giving some English and some French words, and then you'll be prompting the LLM to find to uh, you'll be prompting the LLM to give you the answer, given that you've already given the English word. So that's the few shot prompting in this case. So in this case, since you're given three examples, this is the three shot prompting. And in each context, in the context learning, in conventional is convenient because for the past decades we are using this input output pairs to do any machine learning task. But there's no first principle reason why we have to use input output pair for specific tasks. So when we try to communicate with humans also, we give them instructions, explanation, and teach them and also teach them interactively in addition to provide examples. So that's where our motivation in this comes into picture, where we are giving the output, but also giving a lot of examples so that the model should know what type of output you should be expecting. But again, with the few shot prompting, we have this evaluation problem where we're getting the timing in this which is exact now, but the request that we are getting from the from LLM and that reference is actually is again semantically same but not matching. So what's the temperature, and to ask for weather is again you're talking about the same group, and you will see like in the in few shot evaluation part as well. So in this case, we are just using the Llama 7B and Llama 13B model. And you can see that the exact match evaluation is zero. Even though you can see like the mouse score. So mouse score in this case is a measure of the gap between the neural text and the human text. Just to give you more context, so it is computed using the KL divergence between the two distribution of the text in a more quantized embedding space for the large language model. Yeah, so talking about that, the exact match is actually zero, and that is a concern for us because we want to make sure the most strict evaluation metric should give us at least some number. And that's where we've thought about, why should we just use the natural text when we can change the format of the output itself? And for that, we are using something called the JSON former. So JSON former is a very interesting format where we can actually change the natural text into a JSON format output. And the only thing that we will have to do in this case is just um, yeah, the only thing that we'll have to do in this case is just make sure that you have defined a schema, and and your natural output will always follow that particular schema. So for example, in this particular case, I've given the schema where I've given the request, the weekday, week, time, and request, given that what should be the data type of each of these tasks. And when the output models, like for example, on Friday of week 40, etc., etc., it will be converted into a JSON format, which is going to be much better for matching exact feature, or exact schema of that with the reference that I already have. So in this case, I have converted my output, which is taking the weekday, the week, time, and request, and I'm inputting it in a more JSON into JSON format, because of which, yeah, okay. So now the only thing which I'm changing right now is introducing this JSON format and changing the output format, and you will see how well my evaluation metric has actually changed. So with the JSON format, you can see like the exact match, which was initially zero, that has changed to 75%. And for 13 billion parameters, it's actually changed to 80 billion, sorry, to 80%, which is a very good indication, yeah, that even if even if your natural text is correct, even if you change the output format of it, you will gain significant improvement in your evaluation metrics. So just want to stop here if anyone has any questions here.
Yes, I have a question of like, back to the styling slide, like, it looked like you were extracting some kind of like a sentiment. I was just kind of curious, how is that utilized, as input to the model? Like, is it used somehow as like providing more information or something? Yeah, the slide before this actually,
Oh, this one?
yeah, so it looks like, for example, like, Apple development in-house chips and like the sentiment is tech. I'm just kind of curious, how is that used?
Oh, how is that used in our particular case?
Yeah.
Oh, so this is just an example of what K-shot is. I've taken this from some website. This particular example is not being used in our project. But to give you more context on how this is, so in this case, you can see the prompts are exactly the same, but the output of those LLMs are actually different. So this is like positive, neutral, and negative. And in this case, they are grouping it according to what type of prompt does they actually signify to. So this circulation revenue has increased by 5% in finance. In Finland is talking about some finance related stuff. The second one is sports, and the third one is tech. So that's where, since you've already given the example of finance, it is able to anticipate like what is this particular example is.
Okay, yeah, okay, thank you.
Sure. Anyone else has any questions?
So this table on your slide is claiming or stating that when you have structured format JSON, what is MAUV or MAUVE?
Right. So MAUV score, as I've mentioned before, in this case also. So MAUV score is basically, it's used in the context of like LLMs itself, where so it's an evaluation metric which just checks like how similar are the natural text which is being the natural text which is in the reference, and the human text that, okay, sorry, natural text that has been generated by the large language model, and the human text which is the reference, are close by. So that's the, so it, as I mentioned before, it is computed using the KL divergence between these two distribution of the text, but in the embedding space of LLM. So MAU can actually identify the difference in the quality of the prompt which is being generated from LLM.
Why do you expect exact match? Because the same phrase can be phrased multiple differences, multiple.
Yeah, yes,
ways.
yes, exactly. And that's actually one thing, but and I'll talk about it in the next slides as well, that even though so in this case, where's the evaluation? Okay, yeah. So in this case, even though they are not semantically same, but they are matching, we want to make sure that they're exactly the same, because we want to be as close to the reference or the out to the reference part that the human expects than what we are actually recommending, because this
Oh, so
is
you do want to be literally the same, not
yes,
just
yes, yes. We
semantics.
want it to be exactly the same because we don't want them to again ask for it. Like we don't want them to again ask like what should be the weather or what should be the temperature for this. So there should be no following question, given that you already given the recommendation for them.
Okay, I'm not sure if I follow this part. Let's go on. Yeah, this one I will not get that. Like
So
yeah, the mob score didn't improve much, right?
yeah, the mob score didn't improve much, but the improvement in this case was the exact match, which is going from 0 to 75%, which is just by changing the structure. And the structure is also, it's also happening because in our reference, we can see like the day, which is Friday, and the output, which is Friday as well. So you can see that the matching is happening very nicely. I mean, you can, so in this case, the Friday is matching, 40 is matching, 11 a.m. is also matching, the intent, which is the group, is also matching. And what's the temperature for today, and what's the temperature, which is very same, like very similar, but there might be some changes in this for like which is for today. And exact match, what it does is it will check each and every string in that output and then give you the evaluation. So that's why it's a very strict evaluation metric.
I have a question. The way JSON format works is that it doesn't actually restrict it to the JSON format. It restricts the tokens that it can generate into either numbers or normal strings, right?
Wait, can you repeat that again?
No, the way, because I've used JSON format before. The way it works is that you specify like a type for each JSON field. And
Right,
then,
right.
yeah, and the model can only fill in things that match that specific kind of token, right?
Yeah, so in that case also you should yeah, so the tokens are already matching. That's the reason we are defining those particular attributes, and because those items are matching, it is just filling it with that that schema.
Can't you make it to go to 100 with exact matching trivially by just making the model only able to generate tokens that belong to a specific set, like of the responses you want? So don't let it generate words that don't start with a token that would be a weekday or something. So only let it start.
So
Yeah.
we did try that, but the thing is like the user responses are so diverse that it's not possible to just ask
Okay.
it to do that.
Right.
And you might be asking Alexa to do some task in a certain way, but I might be asking it to do the same task in some other way.
Okay.
Diversity is something that we had to take into consideration as well.
Mhm.
So yeah, let's move forward. We just have like half an. So yeah, so why do I want to provide like examples in the context so that we can improve performances? In this case, the easy way is like it tells the model about the formatting of the output space, but also it is also large enough, and models have signed for life for the profound way. And in this way, I wanted to check like if providing more context can give me better recommendation. And the next part in that case is what I try to do is trying this chain of thought prompting. So this is an example for those who do not know chain of thought. So normally standard prompting is you will give a question and answer, which is what we have in context in K-short learning. We'll give you an example. We'll tell what it should be, what should the answer be, and then we'll ask LLM the same exact type of questions and expect the answer. In this case, you can see the answer is definitely wrong. But if there's a way for my LLM to reason a bit, so that it can know like what's happening behind that, and it will be much better for my model to give a accurate output. And that is something which I wanted to explore as well. So the way I did it is in a very naive way, I just changed the formatting. So let's say if I have this input, I give it to the large language model, and whatever output that my LLM gives me, I'll just concatenate it to the next input. So in that case, what's happening is I'm actually building a temporal information where I'm doing like for Monday for this particular time, so X time. So for time X, for time Y, for time Z, I have these particular actions. Now, can you give me the answer for the next one? And I'm also adding this COT reasoning where I'm the chain of thought reasoning, the considering the progression, what might be the user's action, and it should just involve all the activities and influence from the previous recommendation. So this was a very naive way of doing it. I'm sure like there's definitely better way to have a chain of thought prompting, but in order to make sure like we are experimenting and we are not leaving anything based on just the examples, we wanted to try this, and this actually gave us a good result as well. But then again, what we thought was just by using these types of prompting or zero shot prompting, it's not actually a good way to do it, because there might be a lot of examples that you cannot bring in the input, and there might be a lot of corner cases that might be missed because of that as well. So the baseline which we wanted to work on is just by fine tuning the large language model. So till now we are just using a pre-trained llama model. So in the next part, like what we are trying to do is we're just going to fine tune all the LLM which we already have so now since one thing is fixed, that is the prompt styling. So now since that is fixed, we can start using the fine tuning in a much better way. And for that, the experimental setup was using the LoRa adapter. So for those who are not familiar with what LoRa is, sorry. So this is the architecture. Yeah. So since we have all the features, we wanted to give these particular features to LLM and fine tune it using LoRa, and to get the next action prediction. So again, for those who do not know what LoRa is basically it's an improved fine tuning method where instead of you fine tuning all the weights that constitutes of the weight matrix of any pre-trained LLM, you use two smaller matrices that approximates this larger matrix, and those two smaller matrices are then fine-tuned. So these matrices are constitutes of the LoRa adapter, and it's very interesting. And there's another variant of it which is called QLoRa, which is a quantized version of this particular fine-tuning format. So we used a rank of 64. We didn't really experimented with a lot of ranks. In this case, we just used the rank of 64 and one of 128 as well. But the rank of 64 worked much better. So we just stick with this. So here's the experimental setup. We are experimenting with Llama version 2 of 13 billion parameter and 7 billion parameter. And we are using the output again from the JSON format so that it can give us a better evaluation, like better in the case of exact match evaluation. And as you can see from the table that we have, it's the exact match. It actually increased for 7 billion parameter uh, from the pre-trained model to the fine-tune from 75 to 81, but not that much for 13 billion parameter which is going from 80% to 82%. But although you can see an increase in a lot of other cases where you can see the increase in F1 score, which is 55% for 7 billion parameter, and okay, that should be 13 billion. And yeah, 13 billion parameter is going to be like 57%. So, and the mouse score has also increased in a much better, in a much better percentage from 83 to 95 and 85 to 96, which shows that, yeah, we can have like better performance if you're just fine tuning it with the prompt styling that we already have and using the JSON format that we have. So in this case, you can see the fine-tuned outputs, which is taking the output, which is on a Monday of 10 a.m. The user asked for a coffee break reminder. Um, the same thing, okay, another part, like, okay, yeah, so on a Monday at 11 a.m., the user might ask to play music, which is the reference part, and the output which we are getting from this particular input. If you're putting it in the LLM, we are getting this, the play, just the action, which is play music, which is very same, so which is very close to what the actual output is. So we can see like the output is actually improving. And from this fine tuning, we can observe that with the structured prompts, it gives us a better representation, and the contextual information is also refined during fine tuning, and we can also get better evaluation metrics after this fine tuning. So this was the baseline tool that I tried, but there's definitely a way to make it better. So in this case, what we have proposed is, instead of using just these these unstructured data, if we can make a particular data structure in such a way that all the user actions and requests are in a structured manner, so that it will be it will be much easier for my model to learn and also give me a better recommendation. And for that, I implemented something called a behavior matrix. So to explain what a behavior matrix is, imagine a matrix of 24/7, where we are taking all the days in my row, sorry, on my column, which is Monday, Tuesday, Wednesday till Sunday, and all the timing from 0 to 24. And we will establish it in such a way that it will capture the richness of all the user data. So our approach actually involves a comprehensive analysis of using the raw user interaction data, from which we have actually constructed a behavior heat map that in a given time window, and the user request that captures the temporal and the contextual information as well. So these heat maps are basically just giving me the information of each of particular actions that are being done for that customer on that day for that time. So when we actually try to collate with a lot of customers for a lot of weeks, for let's say for just one month, you will see like few cases, a few elements in this particular matrix will be much higher than the other ones, and that's where. So yeah, so that also gave us a idea of representing this particular matrix as a graph, where the nodes will be representing the users or the interactions, and the edges will be representing the relationship between them. So yeah, so the nodes will be representing the actions, and the edges will be representing the timestamp or the time between them. So this is I'll just go through the proposed method, which I wanted to, which is the main method in this case. So building that behavior matrix, we are actually converting into a knowledge graph. And so the behavior matrix will only have the information about the action, which is, let's say, play music or snooze the alarm, and also the information about the timestamp, at what time or did that happen. The user request is the natural prompt, or the natural request that has been asked from user to Alexa. And I'm using the BERT encoder in order to get the embeddings of these textual information. And so I have not put it here, but so I'm using two BERT encoders, two BERT elements in this case, one for behavior matrix, and another for the user request. And then I'm concatenating both the embeddings in just one embedding. And then I'm using a soft prompt that can be used in the large language model to give us the behavior recommendation. So what does soft prompt actually mean in this case is, like, so there are two types of prompting. First is a hard prompt, which is you just have to type it up, like how you do in ChatGPT. You have to just type it up and just give it to the LLM, and it will give you the answer. In the case of soft prompts, these are basically these are present in the embedding space, and and you have to make sure that these are trained in a particular set of instructions, and not an instruction, as well as some styling, so that you can input it into the LLM. And that is what we did in previous steps as well. So one problem that came into picture with this is the distribution from this BERT encoder is going to be very different than what we have in any LLM. Any LLM, in this case, Llama version 2. So in order to make sure that we are aligned with that, we introduce a novel loss, which is called the alignment loss. So alignment loss, what it will be, in order for us to use that, we just using this alignment loss is nothing, but we just want to make sure like it's aligned with the distribution of the encoder as well as the LLM that we are using. But this was actually very important because without using this loss, we were not seeing any result at all, and we were seeing a lot of hallucinations that were going to happen. So we also changed the evaluation metrics in this stage. We used the rogue score, which evaluates the quality of the summary or the generated text with the reference text. We used the blue score, which also compares the generated text to reference text, but in the based of n-gram overlap. Exact match score, which we already used before, and the precision at 5 or precision at k, which actually evaluates the robustness of for the evaluation of this in the case of imbalanced cases. So when we see this, so the previous two, the first two rows are just the ones which we use from the fine tuning part, where we can see the exact match is 81% and 82%, and the precision at K is also 55 to 57%. But using this knowledge graph and the large language model, the encoder decoder format, we can see that it's actually increased from 57 to 72%, which is a very good improvement. Again, for exact match, you can see it for all the evaluation metrics is actually it's actually increased a lot than just using a fine-tuned part. So that actually gave us this confidence that yes, we wanted a structured part for the input as well. And so that gives us an idea, like, okay, now that we have structured our our input, is there a way for us to learn from that structured input and then give those learnings to my LLMs? Because right now the only thing which I'm doing is I'm just converting all my input into into the embeddings and just giving it just as soft prompt to my LLM. So the proposed method for this particular case is just instead of just just giving the embeddings, I'm going to use a graph neural network so that I can learn all the embeddings. So I can learn all the embeddings from the knowledge graph and then give it to my LLM for a better behavior recommendation. So okay, so just to make sure, for those who are not familiar with graph neural networks, so there are two process in graph neural networks. The first one is the update function. The first one is the aggregation, and the second is the update function. So we are doing the aggregation of all the neighbor features for each node. So that can so that will represent all the features, let's say from user request, from actions, from timing, and then we will be combining those with the transformation that we have. So
So Mrinal, when you run this GCN, it produces you one token worth vector, or it produces you a sequence of tokens that
So
you.
this is actually a sequence of tokens, because the knowledge graph that we have is just not for one customer. It's for, let's say, for millions of customer, and we have represented that in like, so you can see, like, let's say this particular matrix is just for one customer for 1 week, right? Now imagine you have similar, so just for one customer you have, like, for all the weeks that you have, let's say for 4 months, and then again, if you scale it up, you can see just this is not just for one customer, but for thousands of customers. So so we are definitely building the sequence of input, but not just one token.
To Bird. Bird gets entire knowledge graph.
Oh no, so BERT should not be here. Sorry. Yeah, so that's a wrong thing. So instead of BERT, actually, this user request should is combined with the GCN as well. And just giving. I'm so sorry for this. I'm just giving all the tokens that I've learned from the GCN towards the LLM. So BERT is not used in this particular
So
case.
user request is a text or
Yes.
JSON.
Yes. So that's a text. So Let me try to clarify it better. So, okay. So this user request is which is text is going into the BERT, and then BERT is being connected to my GCN as well, because the embeddings are going inside my graph neural network, and the knowledge graph which is already in the like which already have all the embeddings are also inputted to inside the graph neural network. So graph neural network in this case is getting the input from my knowledge graph and also from the BERT embeddings, which is being taken from the user request.
As additional nodes in the graph.
Yeah, as additional nodes in the graph.
The user request, each token enters as an additional node, or you concatenate everything in user request as a single node.
No, I take it as a separate node itself.
The entire user request is a single separate node that you add into the input knowledge graph.
Yes.
Oh.
Not knowledge graph, in combining it with the graph neural network.
Oh, okay. So graph neural network only gets the knowledge graph without user request.
No. So just to clarify it again, I think I should have done this in a better way. So the knowledge graph that we already have, that is being inputted towards my graph neural network. I'm along with that, I'm also giving the user request that I'm getting the embeddings from BERT, and those embeddings that I'm getting from BERT is also are also an input to the graph neural network. So graph neural network are getting two types of input. The first one is from the knowledge graph, and second one is the embedding from BERT.
But user request should be turned into a node in some graph.
Yes. So it is being turned into the into a node in the graph as well.
So you do this, okay, one additional node, it gets connected, and this node has one token that encompasses kind of like all of these tokens that user requests.
Yes. Yeah.
Like you added them or concatenated and turned them into this one token, right?
Yeah.
And then your GNN or GCN runs and returns convergence of a new token for this user, a single token for this
A
user.
single token, yeah, it returns a single token for this particular user, and that is
So I have a question that, that, are you trying to get global information from this graph? Or are you trying to get like, how are you using this graph as like an embedding for your downstream processes?
Can you repeat that again? So just for what I understood is like the global information from this graph, if I'm also like getting the information from my knowledge graph.
So you're basically using this graph to extract some sort of latent representation of, I mean, you're using this GCN to extract latent representation of the knowledge graph, correct?
Mm-hmm.
So and basically, like, how do you create that latent representation? Is it just two layers of a GCN, or is it more complex than this? Because for global context, you need to synthesize the output of a GCN with either like a fully connected network or with global average pooling or something like this. And if you're trying to get like a global representation of this graph, look into how you would do that if you haven't done it yet.
So no, so you're absolutely right. This definitely there are more elements in this particular case. I'm just showing in the architecture like what I have used instead of I have not actually showed like what all the fully connected networks and all those things, because those are not really important for this particular just for showing this. But you're correct, definitely. So in the basic in a more complex graph GCN, right? So I definitely added additional layers. So for example, okay, I think I also added the fully connected network, and I also added the pooling layers for different different types of GCN, which might also be used because I wanted to make sure I'm capturing like hierarchical structures within the graph. and also focus on some specific types of relations. And in order for me to create the latent representation, right, the final layer's output is typically used for that as as the latent representation or embedding of each node. So these embeddings, they capture like both the the intrinsic properties of the nodes and the structural roles within the graphs. So in this case, since my task is for node classification or the clustering, it can I'm also doing a most downstream task, which is the aggregation for each graph level prediction and combining that with the LLM in that case.
Yeah. For node predictions, you probably need less extra layers, but for global information, you'll need more layers.
Right.
Yeah,
That's it.
that sounds really good.
Okay. So okay, so just to continue it again, so I'm in the multi-layer GCNs. My update step is repeated in for several layers, for each layer, potentially having its own set of trainable parameters. In each layer, the node representations are refined based on the broader neighborhood. So I don't want to spend too much time in this, but just give you more context on like what I'm doing in the update function. So given that I have this original feature vector which is of node I, and the aggregated feature vector which are being taken from all the neighbors. So I have this update network which is taking the original feature and the aggregated feature and having this bias vector as well. So that, and then we combine it with, so that is the combine, yeah, then we combine it with the what do you combine with? We combine it with the original feature and then put it into some activation. But one another thing which I wanted to touch upon is the alignment loss, which is pretty important in this case, because the alignment loss in this case is what we are taking are the LLM loss and the encoder loss. So imagine like we have the embedding space from the graph neural network, and we also have the embedding vector from the LLM. Then the alignment in this case is nothing but the similarity metric, or the cosine similarity, which is computed between the embedding of GNN and the LLM, so that we know like the distribution of this is going to be much similar, rather than working in blind with whatever embeddings we have from encoder. Like we don't know like what specificity or where it's actually being focused on. So this actually changed a lot in terms of getting the exact or like proper answer. And the evaluation, as you can see in this case, is from the knowledge graph, we can definitely see that it's 87%, but by adding the graph neural network, we can see the blue score is increased to 91%. Similarly, from precision at K, which is very important metric, it's changed from 72% to 92%, which is a very great jump from the previous method. The exact match has also changed from 89 to 91. Not a lot of change, but definitely improvement. We don't see anything which is a concern in this case, or any validation metric which is going to be low. So we see that this is a improved metric. The only problem with this will be the inference speed, which is going to calculate or give us a proper recommendation, but that is out of the scope for this project. We did more experiments with the large language model variant, where we used different type of different methods and different what do you say, different models also for large language model. Let's say in this case we also tried with 13 billion parameter, and I think we also tried with the Claude model, but the result for this is not present in this case. But let it be. The output for this is the end output that is going to be shown now after I use the proposed method that includes graph neural network. So now this is the output where I have the information of Monday. It's also giving me at what time, like what day, which is morning, 6:30 a.m. Ask for a time, play a cheerful song. For evening, it's giving me the particular request. But now you can see like it's more structured. It's giving me a much more accurate answers, and also giving me an accurate timing as well. So this is just to show like what the output of the recommendation system will be. And this is much better than what we were getting before. So So yeah, this is the project which I worked on. So in conclusion, I just investigated, how different methods on what we can do for user prediction, user behavior prediction using raw user interaction with Alexa. In this project, we also fine-tuned like large language models, and added a particular formatter, the JSON formatter, for so that we can get better results. We also built novel behavior graph, which is so that we can capture the temporal and the contextual information for each user, and also implemented a graph neural network that can learn from this behavior graph and that can also show better results. So yeah, that's all. And right about time as well.
Yeah, very good timing. I'm surprised. I was holding me from telling you, Mrinal, time to wrap up. But yeah, very interesting, but it feels like me and William were missing the actual like deep details. How did you mix?
Yeah, I didn't add a lot of
text,
mathematical
text,
information in this because I feel like there's definitely a deep dive that can happen, because not only in graph neural network but also in the case of like LLMs, there are a lot of equation that we had to build from ourselves, so that we can reach to where we are right now. And the most complex part of this was actually involving this the GCN in this particular architecture so that we can learn this knowledge graph. And we
Interesting.
next, another thing was just to build this behavior matrix, which is a very interesting thing. And I don't think I've seen this anywhere in the literature that I read till now.
Why did you go with GCN instead of just GNN, the RNN style versus?
No specific reason, to be honest. The trade-off that we were following for using GNN and GCN is just like GCN is much better in capturing the context, the temporal as well as the contextual information. Whereas for GNN, it was much better in just use if we are just using the contextual information. So in order to since the temporal information was also very important, so we saw that the GCN was performing better in that case.
Is this in production already and people who talk to Alexa use your method?
Well, as far as I know right now, they are working with some other team so that they can put this in production. I hope it is. Did not really follow up if this is.
Yeah.
But if you see something like this, then yeah, probably. If you see Alexa telling you some recommendation, then probably it is then.
Yeah, so interesting. Yeah, thanks, and I'm glad you got a chance to work on some problem that at this scale.
It's pretty cool.
Yeah,
Thanks.
and thanks for volunteering to present. Yeah, thanks. Okay, bye everyone. See you next week. We don't have a talk right now.